Unlike no other planet in our solar system, Earth is a battleground, a place where two great forces fight for mastery over its surface. Beneath its crust boils a cauldron of molten rock. Within this great smelter are created many of Earth's resources, stone and metals which civilizations have judged to be precious because of their beauty or rarity or usefulness. But the force that builds mountains and creates volcanoes is forever pitted against another, even more immense power, the sun. The fraction of the sun's energy that strikes the Earth makes wind blow and rivers flow. It is the sun that orchestrates the weather of the entire planet. "93 million miles from Earth, a great burning ball of gas warms our planet. Powered by the sun, the elements work to refashion the face of planet Earth. But even in the destruction they cause, a cycle of creation is set in motion, the beginnings of one of the most precious gifts of all, soil. The backs of mountains are broken into rocks and sand and clay. Living creatures and organic matter transform the dirt into soil, living soil. Almost half of each handful is bugs, bacteria, and microorganisms in their habitat of Earth. In life and in death, creatures in it and on it fertilize the soil. Most soil evolves from the weathering of bedrock. But here in the young volcanic earth of the Hawaiian Islands is a most unusual story. Weathering and erosion, the continual shuffling and moving and redistributing of the Earth's surface, is the focus of soil scientists. Carl Uehara of the University of Hawaii has found evidence of just how mobile the surface of the Earth can be. In parts of Hawaii, the soil is enriched by a gray clay, found to be 100 million years old. But there is a curious paradox. The volcanic islands themselves are only 2 million years old.
We suspect that this gray layer is the material that is blown in from the Asian continent and is scrubbed out of our atmosphere by heavy rainfalls. The significance of this material is that it is very rich in potassium and is the means by which much of this vegetation in this area received the potassium for its nutrition.
And so these young tropical islands, in part, owe their fertile soil to the dust from an ancient desert in China, far across the sea. At the end of the Ice Age, the soil in western Tennessee was formed from material deposited by colossal dust storms. The finely ground debris from the wake of glaciers, it is called loess. When early settlers came to this land at the bend of the river, it was covered in thick hardwood forest. They cleared the trees and plowed fields to make the breadbasket of the South, Today, the land is still rich and productive, but it is also victim to severe soil erosion. Each year, over 10 tons of precious topsoil is washed or blown away from each acre of cropland. At that rate, Tennessee loses 1 inch of soil every 25 years. In order to conserve this rich but fragile resource, a new breed of scientists now studies the formation and structure of different types of soil. John Jenkins of the Soil Conservation Service analyzes the overall health of this field by marking off sections or strata called horizons.
7 inches right here, and we have a good subsoil that runs down into the beginning.
Drawing his knife from the rich topsoil to the less productive subsoil to the dense clay below that stops any root or water, he can tell just how productive this soil is. The deeper he goes, the less valuable the land.
We're going to point out the rooting activity zone here. This is your surface layer right here, and if you look, you can see these little roots are pretty predominant, and there's a bigger root down in there. This zone right here is extremely silty, and it's laid down in what we call windblown silt or loess. And this area right in here tends to erode very easily.
The Soil Conservation Service is monitoring the erosion problem. Photographing it from the air is the work of Jim Bilyeu.
Soil erosion is not new. Geological erosion is well known. What happens when man comes along and disturbs the soil material and plants a crop in it? He accelerates the erosion processes.
In the natural order of things, the land will yield to wind and water. But science can help us to use the soil wisely and to slow down the inevitable.
I myself would say that soil is more valuable than oil or gold. You can't eat gold, you can't drink oil and survive, but you can grow food in good soil. So if it comes down to a matter of survival, are we going to have enough to eat, or are we going to have all the oil we want? I'll take the best land every time.
In the mountains of India begins a drama of sun and water. The sun, ultimate arbiter of nature. Not all the erosion caused by its power is for ill. High in the Himalayas, in snow and ice, the river Ganges begins its journey. Water, that liquid essential to life, is sacred in this river. The sacred waters of the Ganges tumble down from the mountains to begin their long descent. To Indians, it is the river of life, and the entire drama of this world is played along its course. As they carve their way through valley and plain, the sacred waters carry organic flotsam, silt, and sand. Where the river meets the sea, much of this matter is trapped together in the huge fantail of the Ganges Delta. Seen from space, the tangled pattern of the delta takes on a new dimension. It is a natural bowl being filled with mud and organic matter carried by the river. The deltas of rivers around the world are places of natural alchemy. In these environments are created coal, oil, and natural gas. The Mississippi River, liquid highway and watershed for the heart of North America. In its delta is deposited the outwash of a continent. Over millions of years, sediments have piled up 10 miles thick beneath the muddy waters. Here, in a natural chemical factory, they are transformed. In the geological magic of a sedimentary basin, organic matter is trapped and accumulates before it has a chance to decay. As the amount of sediment grows, its increasing weight actually presses down on the floor of the basin. And over time, the organic matter is transformed in a natural pressure cooker. Now there must be a layer of impermeable rock laid over the deposit. Without such a cap, the riches of a potential field will simply drift away. As the mighty river flows, the cycle continues. The fossil fuels of the future being formed even as we mine the living matter of the past. Vast deposits of fossil fuels can have modest beginnings. This cedar swamp in Maine may one day be a coal field. Even now it has begun its transformation. As moss and other organic matter accumulates in the low oxygen environment of the bog, gradually peat begins to form, the first step in the creation of coal. In the search for clean burning coal, scientists are studying the formation of peat bogs like these that have low sulfur content. Understanding the conditions under which they form will increase the chances of finding clean burning coal in the future.
Station 4000.
Past her 70th birthday, Cornelia Cameron has mapped peat bogs for the U.S. Geological Survey for the past 30 years. Because the summer months mean slogging hip-deep through the mire, her work in Maine begins early in the spring, while the surface is still frozen.
It's much easier for traveling.
Once through the ice, she uses a coring tool of her own design to sample the thickness of the peat. Sample after sample, she can read the history of the bog. 20 feet of core reveals 12,000 years of history. Beneath the 15 feet of peat are the remains of a forest. Below that, a freshwater pond. And at the very bottom...
Ah, we're in the clay.
The sticky clay was laid down at the end of the last ice age. The sea followed the retreating glacier, flooding this part of New England.
This part up here is in the freshwater pond. The peat deposit that you see all through here was laid down on the marine clay. Many coal beds are laid on marine clay, and then they're covered up. If this deposit was covered up by another invasion of the sea, maybe in a few millennia you'd find coal here, but maybe.
In the search for oil, approximately 3 million wells have been drilled in the United States. Several 100,000 more have been drilled in the rest of the world. The days of wildcatting and gushers are probably over. Today, the search demands a highly coordinated effort of men and machines. Beyond the edge of a continent is a search for oil. 200 miles off the coast of Newfoundland. It was not far from here that the Titanic, the ship that couldn't be sunk, collided with an iceberg and went down on her maiden voyage. These semi-submersible rigs are floating outposts, staffed with crews of over 100 people. Their immense legs contain drinking water, a power generator, a sewage treatment plant, even a small gymnasium. The platform floats in a frigid sea, its ballast constantly monitored and adjusted by computers. This rig cost nearly $100 million to build. It costs $250,000 a day to operate it. But high cost is not the only risk in this hostile environment. Floating mountains of ice the size of city blocks move down from the Sea of Labrador into the North Atlantic. For the past 54 days, this rig has not been able to drill because of sea ice and the menacing presence of icebergs. If an iceberg should collide with a drill rig, it would be certain disaster. Only the constant vigil of men and machines makes such exploration possible. Only modern civilization's great dependence on oil makes it necessary. The long search for oil begins in offices and research laboratories, where science plays a crucial role. Core samples from around the world reveal the histories of ancient environments. They are layers of time etched in stone. Using information from a special satellite, scientists can now learn what hides beneath the surface of Earth and locate places where valuable resources like oil might lie. Guided by a map of the sedimentary basins around the globe and drawing on their knowledge of plate tectonics, petroleum geologists like Don Ziegler and Kerry Mrozowski lead the search. Of the some 600 known sedimentary basins around the world, only about 125 have produced oil or gas. The educated guesses of these men carry high stakes.
In the plate tectonic scheme, the breaking up of the continents, one of the key ingredients is that when the continents split apart, they break on about a 120-degree angle. And one of the breakages will take over, and the other breakage that is left behind is called a failed arm. And because it was a rifting area and subsiding area, it captures a lot of sediments, and it becomes a site that can be very favorable for oil accumulation.
The Sudan in Africa. There are no clues on the surface that beneath the scrub forests and arid landscapes, there might be the structures that trap oil. Seismic studies play the crucial role in deciding whether or not to drill a well. Like sonar, seismic devices probe the Earth with sound. A cross-section portrait of the Earth is gathered from the reflected waves of an explosive charge. Geologists interpret and mark the resulting maps to reconstruct the various levels of the basin as sediments were forming. In the research laboratory, wall map and pens are aided by the very latest technology. The computer slices through a three-dimensional chunk of the Sudan like slicing through a loaf of bread. Each red line, or picking, isolates information that is used to construct a three-dimensional picture of the subterranean world. Like geological time travel, the computer peels back the skin of Earth to reveal part of an ancient freshwater lake. Once flat, it has since been tilted. The slope is color-coded by the computer, from red at the higher end to blue at the lower. It is an environment that could have trapped oil. The tools of science have revealed what human eyes could never see. An important decision is made. The first well was dry, but 1 year and several wells later, commercial amounts of crude began to flow. The exploration in the Sudan is a success, but it is also a preview of the future, a future that will require all the knowledge and tools of science. At the NASA Ames Research Center near San Francisco, a specially equipped aircraft prepares for takeoff. The converted C-130 is equipped as a flying laboratory to test and develop a new generation of exotic instruments.
There's a gravel pit out here. We want to head for.
Scientists know these machines by the general label remote sensing, instruments that see beyond the range of human vision. Developed as sensing devices to radio back information from other planets, these machines provide valuable new insights about the surface of Earth. One of the newest of these instruments is the Airborne Imaging Spectrometer, known by its initials, AIS. It is being tested in skies over Cuprite, a remote mining district in the Nevada desert.
Line start 175351.
Started at 245.
AIS can take pictures of the ground at many different wavelengths beyond the range of human vision.
Looks like the gravel pit's dead.
The reflected light of each wavelength is combined to form a graph, a unique curve that identifies each mineral. The computer is loaded with the graphs of over 200 known minerals. It scans an AIS picture of the ground in a swath 1,000 feet wide and 3 miles long. The computer is able to compare each of the known minerals with the data recorded in the air and actually identifies the different minerals on the surface below. On the narrow map, the computer then colors all the locations of each mineral. The blue, yellow, and red colors seen from the air all relate to minerals found together with gold. In a puzzling development, it also marks the location of a mineral that the computer cannot identify. Guided by the computer-drawn map, two scientists, Alexander Getz of the Jet Propulsion Laboratory and Greg Vane, make the long, dusty trip to Cuprite to look for a sample of the mystery mineral.
Yeah, the ratios look good. I think we're right on the money.
Okay.
Looks pretty good.
It looks no different from dozens of other rocks lying about.
Oh, yeah.
But the spectrometer indicates this rock contains the mineral they are searching for.
Uh-huh. That's probably a sample we ought to take.
When analyzed by the U.S. Geological Survey, it will prove to be a rare discovery of an obscure mineral called Buddingtonite, a possible pathfinder for locating deposits of gold. Alexander Getz.
Remote sensing measurements will never replace the geologist in the field. But with the new instruments that we have now, the new kinds of measurements like imaging spectrometers, and in particular the airborne imaging spectrometer, we can make measurements that allow us to see things that can't be seen by the eye or can't be seen by a geologist.
This kind of remote sensing will speed up mapping of minerals on the surface by orders of magnitude. What once took years by conventional methods can now be done in an afternoon, and with far greater detail than ever before. Flown on the space shuttle and on a space station, AIS has the potential to map for the first time the surface minerals of the entire United States and perhaps the world. As we begin to acquire a global perspective of the Earth's great gifts, this new technology allows us to see our world in a completely new way. Probing with electronic eyes, satellites reveal the face of an Earth at once familiar and unexplored. We know little of what lies beneath these rugged landscapes and icy terrain. It is clear that the metals and minerals of this restless Earth are being used more quickly than they are being created. If civilization is to continue in its present form, the search for new discoveries will go on, possibly even beyond our own planet. In that search, there will be yet newfound knowledge about the wondrous ways the Earth is shaped and formed. And perhaps the most precious discovery of all will be a new understanding of planet Earth.